Okay, so I'm back on this hypothesis test problem about the restaurant chain and whether the employees are are stressed, I think. So I'm going to go ahead and mark on here where my sample proportion falls. So 0.68 would be about halfway between 0.66 and 0.70. So right about there. And then I'm interested in it being more extreme than that. So I shade to the left. Okay. More extreme would be even lower. So again, that is the probability that p hat is less than or equal to 0.68. Okay, so let's go ahead and fill in my work here. So I have z is equal to, and I'm filling in my p hat is 0.68 minus my parameter p is 0.75 divided by the square root of 0.75 times 0.25 divided by 100. Whew. Okay, I know I already calculated this to be 0.043, but I want to make sure I don't have any rounding errors, so I'm going to enter it as a whole thing again. So don't forget to put parentheses around the top when you enter this into your calculator. So parentheses 0.68 minus 0.75 end parentheses divided by second square root 0.75 times 0.25 divided by 100. Whew. Okay, so I get negative 1.6. Remember, this is going to be a z-score I'm going to look at in table A2. So I just need to round to 2 decimal places, so it's negative 1.62. Negative 1.62 is my z-score, or my test statistic that I'm going to look at table A2 to find my left area for. Okay, so let's look at table A2. I need to be on the on the negative z-score side, so let's flip over. Negative 1.6, I line up here with 0.02, so negative 1.62 is 0.0526 is the area to the left. Okay, so I'm going to write that I used table A2 gives me a left area equal to 0.0526. Now, this is where that two-sided test comes in, right? This is a hypothesis of, an alternative hypothesis of not equal to. So it could be this low or lower, or they're interested if it were on the other side, that high or higher. Okay, so notice our z-score was 1.62. Sorry, negative 1.62. So it was about 1.5 or 1.6 standard deviations beneath the mean. The other side would be about 1.5 or 1.6 standard deviations above the mean. That would be the equivalent distance of 0.68 from the mean if I were above it instead. So I want to do that or more extreme, so or higher. So what I'm looking for to see if it's different is this area plus this area, which this is a symmetric curve. If I drew it better, they would look exactly symmetric. So I should just be able to find this left area and multiply it by 2. Well, I've already found that left area, right? These two are the same thing. So I can multiply that by 2 to come up with my ultimate p-value. So it should be 0.0526 times 2, which is going to give me 0.1052, if I type that in my calculator. Okay, that is my p-value. So notice, if I had done a different hypothesis, well, actually, that's not true. If my hypothesis had been p is less than 0.75, my p-value would be 0.0526. But since it's different from, I have to multiply that by 2 to get 0.1052. Oh, so it is true. I forgot my significance level is 0.1. So if I just done a left-tailed significance test, just the less than, I would reject the null because 0.05 is less than 0.1. But since I'm doing a two-sided test where I'm saying p is not equal to that null value, then I have to multiply that original p-value by 2 and I get 0.1052, which is greater than 0.1. So I do not reject my null. Okay, so let me write that down, make it a little bit more clear. Since my p-value is equal to 0.1052, which is greater than the significance level of 0.10, we fail to reject the null. Fail to reject. Right? This is not unusual enough to think that the null is wrong. So we say we do not have convincing evidence that the proportion of this chain's employees who would answer yes is different from 0.75. Okay. All right. And again, I got this last part from the specific problem, right? I'm going back and saying that we do not have convincing evidence that the proportion of all employees in this chain who would say yes differs from 0.75. Okay, so this last part, number 2, is actually not a part of the hypothesis test at all. It gives a little bit of insight into how we use confidence intervals in conjunction with hypothesis tests. Your book talks about this a little bit more. It actually phrases confidence intervals as a way of constructing a hypothesis test, but we will not be using it that way. We'll still be using it as more of an informal claim. So it says a 90% confidence interval for the restaurant worker data was also created and found to be 0.603272 to 0.756728. Okay, so basically like 60.3% to 75.7% or so. Let's notice that it's a 95% confidence interval. So a confidence level of 90% corresponds to a significance level of 10%, right? This middle 90% has 10% on the outside. It's kind of the idea that they're going for there. Okay, so explain how the confidence interval is consistent with, but gives more information than the test. So instead of writing this one out, I'm again just kind of going to show you what I am going to write. I would say that the null value of 0.75, right, the value that I assumed my proportion is within that interval, right? 0.75 is less than 0.756, so it's within this interval. So 0.75 is a plausible value. Remember, the confidence interval is the plausible values. But it gives more information than that. The interval also gives other plausible values for the true proportion of employees who would answer yes. Okay, so it's possible that 75% is the true proportion, but I'm seeing that it's possible it could be anything between 60 and 75%, according to this confidence interval. So it's not like I've proven that 75% is the true proportion. I cannot know that. All I am doing is saying that I don't have evidence that it's not 75%. A little anticlimactic, but it is what it is. Okay, that's it for hypothesis tests. Make sure you answer the question on you ask a question on the discussion board and read through your classmates' comments to see if they ask any good questions as well.